This example is a conservation of energy question. It's example 2. What we've got is a 150-gram ball is attached to a vertical spring. Okay, so the diagram in the slide looks something like this. It's in the vertical position. So this thing's going up and down. The ball is free to kind of go up and down. It's an ideal spring. It's compressed 14 centimeters above equilibrium. Okay, so this distance in here, 14 centimeters. It's then allowed to fall. It's going to pass right through equilibrium. And the question is, how fast is it going when it's 18 centimeters below equilibrium? All right, the slide showed that this was x equals 0, and I just want to stress that we are not free to choose where x is 0. We're not free to choose where equilibrium is. We just have to know where it is based on the question. So I'm going to put it here in the middle. What I'm told is it starts off 14 centimeters above equilibrium. Okay, so what we're doing is we're starting off up here, 14 centimeters. I'm going to convert it 0.14 meters. It starts off 0.14 meters above that equilibrium position. It's allowed to fall. It's going to pass right through equilibrium. It's not going to stop there. It's going to continue on. And then the question is, how fast is it going down here when we are at a position that is 18 centimeters, 0.18 meters? And I'm going to stick a negative sign in there. So I'm 18 centimeters below equilibrium. Okay, so I mentioned this on one previous slide, but if you didn't catch that, I am always going to choose up as positive for conservation of energy questions. It is possible not to. It's possible to choose down as positive, but you got to remember a few things about height and some extra negative signs that we need to kind of spice in there. To avoid any of that stuff, I'm always going to choose up as positive. My recommendation is do that as well. Choose up as positive always in energy, in conservation of energy. If you want to ask me about ways to not do that, you can ask, and I'll go through that separately with you. The next thing is I want to choose where my height is going to be 0 because I need to consider gravitational potential energy as well. Gravitational potential energy, the height, we are free to choose where height is 0. Okay, we're not free to choose where x is 0, equilibrium, but we are free to choose where h is 0. We've often done lowest point, h is 0 down here. We could do some calculations. I'm going to make the argument that this time it's actually a little bit easier. If you're being lazy, it's a little bit easier to choose h is 0 when x is 0, because that means these values are going to be the same. Okay, so this is going to be true. This also negative 0.18 meters. Okay, and I made a big deal about this negative here. If you think of our equation, let me write it out now. Our conservation of energy equation is the big whole monstrosity. Looks like this. And you might say, it doesn't really matter if x's are positive or negative because they're squared. You're right. It does matter if your h's are positive or negative, though. I'm going to put this in as well. I'm going to put the whole big equation here, just so you can see it all in all of its glory. Really, when I do one of these questions, I consider all of these things. Okay, so if you don't want to write the whole thing out, that's fine, but at least consider it in your mind. These are all the things. So when I'm making a diagram and I'm considering, what's h1, what's x1, really what I'm doing is I'm picking all these variables out. Is there an applied force? Is there x1? Is there h1? Is there a v1? This thing says it's allowed to fall. That to me says that v1 is 0. When it's allowed to fall, it also says to me that the applied force is 0. Okay, so I'm not pushing on this thing. I just drop it. I let it go. Same idea down here. What we're looking for down here is what is v2. Okay, that's the speed that we're looking for. They also mention no friction. Okay, so there's no air resistance in here. In real life, of course, there's friction. They don't mention it. We're just going to ignore that. Okay, so because of these zeros, the most exciting part of one of these questions is canceling stuff out. That's always fun. So V1 is 0, that's gone. FA is 0, that's gone. Down here at the bottom, friction is 0, that's gone. Everything else looks like we've got to consider it in there. Really, at this point, it's kind of like the physics is done. Now it's just the mindless task of subbing all the numbers in. Okay, so I'm always going to recommend draw a good diagram, give yourself enough room, consider sort of all the 4 variables of the left-hand side of the equation, all 4 variables of the right side of the equation. Write down everything, always choose up as positive. Once you can get here, let's just sub in and solve. So this is pretty easy now. Mass, One last, I guess, trick, if I can say there's a trick. Make sure to put that in kilograms. H1 0.14. K is this thing, 12.1. X1 0.14. Mass. V2, we don't know what that is. Mass. Again. H2, remember these signs here are very important, so make sure you get that sign. Negative. This one, for good communication, can you see this still over here? Yep. For good communication, I would say put the sign in here. We're going to square it, so it doesn't really matter. But for good communication, put that negative. This one you have to have, otherwise you get the wrong answer. We're going to calculate all this out. Let's see, I've done that here. 0.787. That is these things and these things kind of brought over to the other side. This guy here, oh, and the half, I took care of the half. So now I'm down to this. So I did a lot of math there. I did this thing, found the number, this thing, found the number, added them, find the numbers, bring them over. I also multiplied both sides by 2. Okay, so I did a bunch of math there. Now we're going to rearrange, solve for just V2 on its own. V2 is 2.3 meters per second, at least approximately. This thing is a speed, just keep in mind. We could say when you first let it go, it's on its way down, but this would also be the speed whenever it reaches the lowest point. When it comes back up and again reaches this position, it'll again be going this speed. So this speed, you could argue it's down the first time, but it's up the second time, and you know, it's just going to keep kind of going up and down.